Hello students, this is part of our physics of motion study. Today we are going to look at the concepts of speed and velocity. Earlier we were looking at the idea of displacement versus distance. Now what we're going to do is look at distance in a certain amount of time, or displacement in a certain amount of time, which we are going to call speed or velocity. These are components of motion. It's common to hear things described as moving slow, fast, quick. We are much more interested in quantitative measurements rather than qualitative descriptions. So one quantitative measurement is speed. This is defined as the distance covered by an object in a given amount of time. In equation form, we could say speed equals distance divided by time. One of the things that we're going to have to be very careful about in this course is that whenever we use an equation, it not only has numbers, it also has units of measurement, which I will often just call units. You could have miles or kilometers or centimeters or light years for distance. You could have hours, seconds, days, centuries for time. So there are a whole host of different units that are legitimate for describing speed. Because of this large variety, which would cause a lot of confusion among beginning physics learners, let's agree that most of the time our measurements will be in meters per second. Although in this particular presentation I will have several that are kilometers per hour or miles per hour, since those might be more familiar units for you. As an example, if a cheetah covers 50 meters of distance in a time of 2 seconds, then its speed is distance divided by time. The answer is not 50 divided by 2 equals 25. It's 50 meters divided by 2 seconds, which equals 25 meters per second. You have to have those units of measurement as well. Because we live in the United States and use the imperial system of measurement, the metric system is not very familiar to many of us. So 25 meters per second may not mean a lot to you. If you look at this chart, you can see on the very left-hand side some miles per hour, and then on the right some equivalent meters per second. What you will see is that you can take the magnitude or size of the miles and divide by 2, and the meter per second will be just a little bit under that number. So for example, 50 miles per hour equals 22 meters per second. There is, of course, a more precise way to get the exact equivalents, and there are devices and calculators and apps that can do it for you. The speedometer shown on the screen here has both miles per hour and kilometer per hour scales side by side. Neither system is better than the other in the sense that they can both measure speed. What makes the metric system more convenient is that everything is based on the power of 10, and the measurements themselves are based on nature, not on arbitrary decisions. For example, what is a mile? How many feet are in a mile? How come? There's no good answer to those questions. They are just historical accidents. The meter, on the other hand, was established to be a certain length. That length has been refined over time, but it was based on a natural measurement, not on an arbitrary measurement. One of the things you know if you've ever observed the speedometer in a car is that your car does not always go the same speed. What the speedometer is giving you is something called the instantaneous speed. the speed at a particular moment. There are other speed values or calculations that we could do, such as the average speed. If we're in a trip in a car, we might want to know our average speed so that we can estimate our time of arrival. The average speed is the total distance divided by the total time of the trip. For example, if we traveled 240 kilometers during 4 hours of time, our average speed would be 240 kilometers divided by 4 hours, which equals 60 kilometers per hour. But though we are averaging 60 kilometers per hour, that doesn't mean we are always going 60 kilometers per hour. Our average speed and instantaneous speed can be quite different. Instantaneous speed is what earns you a ticket if a police officer finds that you are going too fast, not your average speed. So, in either case, if we're talking about average speed, instantaneous speed, or a constant speed, we are talking about a rate at which distance is traveled. That term rate is going to become very important in our course. This is the first rate that we have encountered. Now to drill down on the mathematics just a little bit. Our equation for speed is distance divided by time. Rather than have to write out those words every time, it's very common practice to use letters to substitute for the variables in an equation. So we could, if we wanted to, just pick the first letter of each word and write an equation as shown on the screen. S equals D over T. I wouldn't write that down just yet because it turns out we really don't like to use S to stand for speed. Though we certainly could use S to stand for speed, we usually do not do that because S is often used in older textbooks to stand for distance. I know there's no S in distance, but the S came from the Latin word for distance, which is spatium. So sometimes we do not use the first letter in an English word for our variable. Instead, we may use a letter that comes from a foreign language. We might even use letters from other alphabets, such as the Greek alphabet. So if we are not going to use an S for speed, what are we going to use? Answer: more often than not, we will use a V. And the reason is that the velocity equation and the speed equation are very, very similar. So we might as well use the same letters. Now, what is velocity versus what is speed? We'll cover that in just a second. But I do want to make a little note here that, again, the letters are totally arbitrary. And even though we might try to standardize them for this course, that does not mean they are standardized across the entire spectrum of physics or science or society. The online textbook that we are currently using, for example, often uses an X instead of a D to stand for distance. The reason it does that is because it might be measuring distance along the X-axis. Now I'd like to show you a little trick that you may not be familiar with. I call it the magic math triangle. If you have a 3-variable equation or a 3-letter equation as shown here, what you can do is draw this triangle and put the letters inside the triangle, and then you can manipulate the variables very easily when asked to find any unknown. So what we are going to do is take them and put them into 2 of the boxes in the triangle. And since the D is over the T, we'll make sure that the D goes on top of the triangle. It really doesn't matter which of the 2 boxes below you put the T in. Seeing as there is an empty box available, we will put our last variable in that space. So now we have a magic math triangle for the speed equation. So you can take any equation and find ways to manipulate it and make solving problems and book problems a little easier. That's all we're doing with the magic math triangle. Anytime we have an equation, a problem that says what is the speed, what is the distance, what is the time, we can use this magic math triangle to figure out our equation very quickly and therefore get the correct answer. Just as an example, let's say we want to find the distance that something travels. Since distance is the unknown, we will take it out of the triangle first. Now look at the remaining variables. How are they related? They're beside each other. So let's write them beside each other in our equation. We'll take the v and the t out and put them side by side. And we will multiply them with a little dot since they are side by side. You don't have to use a dot. You can use an X or an asterisk or nothing at all, as long as you understand it is speed times time. So again, what this equation represents is a way to figure out distance when given speed and time. We take the unknown, distance, out of the box first, and whatever's left, we write it into the right side of the equation, however it's related in the box. For example, let's say that the average speed is 80 kilometers per hour. That's the v. And we are on a 4-hour trip. That's the t. What is our distance? How far will we go? Distance equals speed times time. So it equals 80 kilometers per hour times 4 hours. It is not 80 times 4. It's 80 kilometers per hour times 4 hours. The 80 and the 4 multiply and give you 320, but the kilometers per hour multiplies by hours and gives you kilometers. So we get a distance unit. So the answer is 320 kilometers are traveled by an object going 80 kilometers per hour on a 4-hour trip. Think about this problem. If a cheetah can maintain a constant speed of 25 meters per second, it will cover 25 meters every second. So at this rate of speed, how far will it travel in 10 seconds? What about in 1 minute? When a question says how far, it is asking us to find distance. So we take distance out of our magic triangle. We see that v is beside t. So distance equals velocity times time. If we look back at our problem, we see that we are given a velocity 25 meters per second, 25 meters every second. And we are asked in a time of 10 seconds, how far will it go? So distance equals 25 meters per second times 10 seconds equals 250 meters. What about in the second case? If you simply multiply by 1 minute, then you would get an answer of 25 meter minutes per second. That won't do. So we have to convert minutes into seconds so that all the time units will cancel out, leaving us only with distance units. So there are 60 seconds in a minute times 25 meters per second times 1 minute, and that gives 1,500 meters. Your units in your final answer should match the unknown variable you are looking for. If you've paid attention to the instrument board of your car, right next to or right below the speedometer is an odometer. An odometer tells you how many miles or kilometers you have traveled. So if an odometer reads 0, well, maybe you have a trip A or trip B setting and you set it to 0, and later you find that you've gone 35 kilometers and it required a half hour, what was your average speed? If we look at our magic math triangle, what we are trying to calculate is speed. So we pull the v out. That leaves the d over the t. So our equation is speed equals distance over time. Now we can substitute in our values. We can say this equals 35 kilometers and 1/2 hour. I put 0.5. Put that in your calculator in case you can't do it in your head. The numbers give you 70, but the units give you kilometers per hour. So the correct answer is not 70, it's 70 kilometers per hour. So earlier I mentioned the word velocity. Speed and velocity are related, but they are not exactly the same thing. Speed is a description of how fast an object moves. Velocity is how fast and in what direction it moves. So while in everyday life you might use the terms speed and velocity interchangeably, in physics, velocity has a very particular meaning. It is speed in a given direction. We say that a car travels at 60 kilometers per hour. That's speed. If we say 60 kilometers per hour to the north or past our house or some other direction, then we are specifying its velocity. Now you might think that's a very fine distinction that makes hardly any difference. However, it makes a huge difference. Anytime you have a quantity that is just a magnitude, that is a scalar quantity. But if it requires a direction, we call it a vector quantity. And the difference is very, very big in real life. Vector quantities are what we might call state functions. They only depend on starting values and ending values and not really what comes in between. Whereas scalar quantities measure everything that comes in between as well. I'll show you what I mean with an example in a moment. Here's one way to see the difference. If I say something is going at a constant speed, that means anytime I check its speed, the number will be the same. But if I say it's going a constant velocity, not only is its speed the same, but its direction is the same. It's going the same straight line that it was going before. If either the speed or the direction or both are changing, then velocity is not constant. It is changing as well. Later, we will learn that any changing velocity is known as an acceleration. So, as an example, if you had a body moving at a constant speed, but it is turning, it's not going in a straight line, then it does not have a constant velocity. Here's an illustration of that point. This is a car, and if we imagine that it's going at a constant speed, say 60 miles per hour, it does not have a constant velocity. Because it's going in a circle, its direction is constantly changing. So even though its speed is constant, its velocity is not. So imagine this scenario. The speedometer of a car moving northward reads 60 kilometers per hour. It passes another car that is traveling in the opposite southward direction at 60 kilometers per hour. Do both cars have the same speed? Do they have the same velocity? They do have the same speed, but they do not have the same velocity. In fact, you could say that they have opposite velocities because they are moving in opposite directions. In fact, if you use this on a problem on a piece of paper, you might designate one direction, let's say northward, as positive, whereas the other direction would then be indicated with a negative. So keep in mind that while we use the same letters to stand for speed and velocity, they actually measure different things, especially with regards to the D. In speed, that is distance, a scalar quantity that does not depend on direction. But with velocity, D stands for displacement, which, if you'll recall from the earlier lesson, displacement is a straight line measurement from start to finish. So to see how that plays out, consider this scenario. A car travels 40 kilometers north for 1 hour, then travels south 40 kilometers for 1 hour back to its original starting point. What is the car's average speed? What is its average velocity? In the first case, speed equals distance over time. We could write v equals d over t, but d stands for distance. Distance does not regard direction, so it travels 40 kilometers one way, 40 kilometers the other way, a total of 80 kilometers. It takes it 2 hours to make that trip, so 80 divided by 2 gives an average speed of 40 kilometers per hour. What about its velocity? Velocity equals displacement over time, and displacement is a straight line measurement from start to finish. So in the first leg of the trip, it goes 40 kilometers. In the second leg of the trip, it goes 40 kilometers in the opposite direction. To show it is opposite, I'm going to indicate southward with a negative sign. 40 plus a negative 40 equals 0. So the velocity, the average velocity of the car for the entire trip is 0. Huge difference. That's why it's extremely important for you to distinguish between distance and displacement. Those are scalar and vector quantities, and they give vector or scalar quantities as a result when you use them in other calculations. So in other words, speed is a scalar, distance is a scalar. You do not have to consider direction. Velocity and displacement, on the other hand, are both vectors. You have to measure start to finish in a straight line to get displacement. In this case, it ended up right where it started, and therefore its average velocity is 0. So I hope you can see that speed and velocity are not entirely equivalent. Velocity involves speed. It is speed in a given direction, but it is not equivalent to speed alone. Now you should look for some opportunities to practice. Thank you for watching.